All right. Hello, everyone, and thank you for joining us today for the last session of the semester of our Parks College weekly webinar series. My name is Amy, and I'm the Outreach Coordinator at SLU's Parks College. I'll be joined today virtually by Dr. Guru Rajan, who will be showing us around the Aerospace Engineering Program's AirCRAFT Lab. We are very excited to have you joining us today from wherever you are. Thank you for taking the time to virtually visit us and learn more about the aviation and engineering programs at St. Louis University. In total, Parks College has programs available in aerospace, biomedical, civil, computer, electrical, and mechanical engineering, as well as flight science and aviation management and physics. We hope that you will hear or see something today that piques your interest. Throughout this webinar, we do encourage you to submit any questions that you may have to the Q&A feature at the bottom of your screen if you're viewing through Zoom, or in the comment section if you're viewing through Facebook Live, and we'll do our best to answer as many questions as possible during the last few minutes of our session. Throughout this webinar, you don't need to worry about turning off your microphone or camera. You can hear and see our presenters throughout the webinar, but we cannot hear or see you. This session will be recorded and posted to our YouTube page in the next few days. You'll receive an email with that link when it becomes available. If you would like to view any of our previous webinars, you'll also find those recordings in both a Fall 2020 playlist and a Spring 2021 playlist on our YouTube page. So now with that information out of the way, I'm going to pass it over to Dr. Guru Rajan and the AirCRAFT Lab. So Dr. Guru Rajan, I will let you take it from here.
Thank you, Amy. Thank you for the introduction, and welcome to everybody who's on Zoom and on Facebook. As Amy said, my name is Shrikant Guru Rajan, and I am an associate professor of aerospace engineering here at Parks College, St. Louis University. So what I'm going to be talking about today is the work that we do in my lab. My lab is called the AirCRAFT Lab. The AirCRAFT Lab is a recursive acronym, and basically it stands for Aircraft Computation and Resource Aware Fault Tolerance. So the goal or the story behind everything that we do in our lab is how do we keep our drones safe when they are flying in the air. So these are mechanical systems. Okay? So most of the time, it's not a matter of if, it's a matter of when and what causes it to kind of fail. If it fails on the ground, nothing's really lost, and you can take it to your shop and fix it and go back and fly again. But more important things are like what happens to your drone if something goes wrong while it is flying. Okay, think about Amazon trying to deliver your Xbox. Okay, and halfway through the delivery process, hey, something happens to your drone, and something breaks on your drone. Okay, so now the question becomes, how do you keep the drones safe and stable when something breaks? Okay, so that is the crux of the main driving force behind the research that we do in our lab. I'm going to share my screen in a second. Screen. Can you see the screen?
Yes.
Okay,
yeah, we
cool.
see the PowerPoint.
Okay, so this, let me just make sure that it plays. It's supposed to play. So as you can probably see in the thumbnails, I'll talk about it and then we look at the entire slides as it loads. I didn't expect it to take a long time to load, but we work with drones of all kinds. So we work with both fixed-wing airplanes and fixed-wing drones, as well as multi-rotor drones. Okay, but what you see in the background, if you can see the airplanes that are on the table, these are our workhorse fixed-wing drones. Okay. So
hey, Dr. G, just so you know, we can't see you anymore or your camera.
You can't see my camera anymore? Oh,
Now I see you in the.
okay. Yeah, I
There you
think
go.
I have to share because I'm sharing screen and whatnot. It is okay. So let me switch cameras. How do I switch cameras? There you go. Okay, let me just talk through it. So can you see the airplanes?
Yes. Are you there? Perfect.
Yeah. Okay. So okay, can you see the airplanes now?
Yes.
So this airplane, we call it the sharpshooter. It's got a history behind its naming, but it's named after an insect. It's called glassy wing sharpshooter, but that's what we call our airplane. So this is our workhorse airplane. And the thing is, we designed and built this airplane ourselves from scratch. And the fun thing is this is not purely a remote controlled airplane alone, like a toy airplane, but this is a research platform. And I will show you what's inside this platform. So inside, you will see the guts of the airplane, which is pretty much all the electronics that's inside it. It includes a flight controller and a data acquisition system so that we can collect all sorts of information about the airplane when it flies. Okay, so over here, for example, you see two GPS antennas, which we use to collect the position velocity of the airplane, as well as the time that GPS will give you. So inside this airplane, we have this computer. Right now it's outside so that it's easy for everybody to see, but this is a custom designed computer. So what this computer does is to collect all kinds of information that tells us how the airplane is flying. For example, like I was saying about GPS will tell you, where the airplane is, how fast it's flying, which direction it's headed in, and so on and so forth. That's important information. The other things that we collect from our airplanes are information about its airspeed. And you see these two weather vanes, they are called aerodynamic flow angle sensors. Okay, so they will give you an idea of what's called the angle of attack and the angle of side slip on the airplane. Okay, and this computer has more sensors on it. And what they record are things like, how fast the nose of the airplane is going up or down and things like that. So all in all, we collect maybe about 25 different sources of information as we fly our airplane. Why do we need this? So what we do with all the information that we collect from the airplane is to do what is called parameter estimation, which means we are now trying to figure out the model, the mathematical model of the airplane from the way the airplane flies. And if you can maybe see what's on the whiteboard, that is pretty representative of what an actual airplane ends up being. Okay, so so that's what we try to do with our airplanes. What does it give us? What it gives us is an idea, or it gives us enough information to run these airplanes in software so that when we run simulations, we can do all kinds of things on a simulation. Okay, for example, we could say, hey, this thing broke on my airplane. Okay, I don't have any more elevator control on my airplane. So how does my airplane fly? You can test it out in software. And that's what we do. We run through these tests, different scenarios where we artificially inject different kinds of failures on the airplane. And we run all these things in software to see how the airplane actually behaves. But that's not where we stop. Once we run this in software and if we figure out how it behaves, then we go ahead and fly the airplane and inject these failures in real flight. And then we have control algorithms on the computer that you saw earlier, the green computer, that one, actually, this one again. So we have control algorithms that are on this computer that will be able to detect that, hey, something's wrong on the airplane. It's not flying the way it's supposed to be flying, or it's not flying the way I know it should fly. Okay, and then it will identify, okay, I think the reason behind the way the airplane is flying this way is because the elevator on the airplane is stuck. or the elevator on the airplane is broken, or something like that, okay? So, and then the computer will be able to figure out what to do to reconfigure everything on the airplane so that it's flying normally, okay? But these are all, in a sense, pretty boring kind of failures, okay? I hope, a few of you have had a chance to build things by hand. So a few years back, I had a student in my lab who came to me and he said, hey, Dr. G, I have built potato cannons when I was in high school. We used to do that for fun. So, once you build a potato cannon, you get a couple of brownie points with me in my lab. You know why? Because you get to do this. So what we do is to build these airfoils, okay? Now these airfoils we have 30 of these airfoils. They match the wing on this airplane, okay? And this actually matches the wing on the airplane. And then what we do is we take the air cannon, the potato cannon that my students built, and we fill it up with ice pellets. And then we take a shot at these wings. Again, this is all done on the ground. We put the wings in a separate jig, and then we poke holes at the on the wing. And you can see, if you pay close attention, these are all marked. They all have numbers on it. So what we do is to now think of situations where you're flying these drones, and then it gets into a hailstorm. What happens to the wings of the airplane when it gets into a hailstorm? You're more than likely going to come up with a wing that looks like Swiss cheese. Actually, we call these wings as our holy wing with an E. So, and then what we are doing right now is to figure out what happens to the way the airplane flies. How does the airplane fly, and how does it, is there a change in the way the airplane flies if there are holes in the wing? And are there ways that we can figure out what exactly went wrong on the wings? So the answer to both are like, yes. We can figure out how, what actually is wrong with the wing. And that is actually some of the stuff that my students are working on right now. What do we use? We use the next kind of sort of the most sought after topic, if you can call it that. It's AI and machine learning. So we use artificial intelligence and machine learning techniques to figure out the pattern of these holes on our wing based off of how the airplane is flying, based off of flight data. So that's one thing that we do. What else is here? Let's go back and switch cameras. So this is with the fixed wing airplanes, and we have multiple airplanes. And as you can see, the bigger platform with the orange tail is designed for classroom instruction. Okay, so I teach classes on upper level classes on what's called flight dynamics and flight controls. And this airplane is designed to be used within the classroom. So, what we can do with this airplane is change a lot of things on the airplane. We can change the wings on the airplane. We have a process where we can chop the tail off of this airplane and put a new tail on it and figure out how the airplane will fly differently if it's got a different configuration. So we can talk about it in class quite a bit. But when you go out to the field and actually test it out, it makes your understanding so much better. Okay, so that's what this other big airplane is for. Like I told you before, we work on both multi-rotors and fixed wing airplanes. And what you see here, there's a big one on the floor, and there's another one here. So this is a hexacopter, but if you pay a little close attention here is what's called a 9-axis accelerometer that is attached to the arms of the hexacopter. So why do we need this? And what is the goal behind that? So what we are trying to do is to see if we can track the vibration profile from the main computer that's over here on the inside. If we can use the accelerometers to figure out how if there's vibration profile that we can use to detect any problems that we may have on these arms or on the propeller, for example. Let's look at the propeller here. You see what's happened here? So this one was an artificially induced failure. So what one of my students did was basically take the propeller to the sidewalk and with a hammer. So, I hope you get the theme in my lab that we build things and then we go out and have fun and kind of break them to make sure that these things don't break when you're flying it for real. So we did this, and then we are working on techniques, again, using AI and machine learning to see if we can detect the change in the way the airplane flies because of this failure. Okay, so that's a couple of things that we do here. Okay, and a big thing in my lab is that if you join our lab, you get to build these things for sure. Okay, even if you don't necessarily have the skills to begin with, you start at some point and then you start gaining the skills that you need. Now, let me show you some of the work that we do with multirotors. How many, I hope a few of you have, let me share screen. Hang on a second. While I try to get my PowerPoint up and running, if you have any questions, I'm happy to answer while that is getting ready.
Yeah, so if anyone has questions, feel free to submit those to the Q&A or to the comment section if you're on Facebook. Dr. Guru Rajan, I was wondering if, so you were discussing like kind of the future of package delivery using drones, and I know, in some cities they've started testing that. Do you see that as part of, the major application of drones in our everyday society, or are there other ways that they'll be built into our future lives?
I think drones are going to be in everything that we see in the future. Give it another maybe like 5 to 10 years and you are going to see air taxis where you just, it's like an Uber. Actually, Uber has a program for air taxis where you just pick up your smartphone and dial in or ask for an air taxi, and you have this autonomous drone come in and land right next to you or at a particular pickup station or something like that, and then it takes you from one hop to another within a city. So that's a big area of very active research in aerospace engineering. It's called urban air mobility, UAM, and that's a very big area of current research. And then you have other things like, when you have drones, you don't have to worry about, being out in the cold or being out in the sun and things like that. And you can task your drones to do the things that are either too strenuous for you, too boring for you, or it's just going to take too much effort on your side. Okay, so things like monitoring how your crops are growing, for example, or things like how is your orchard growing? How is that orange tree that you really, really like in your orchard? How is that growing? So a farmer, for example, can have access to drones like these and be able to go in and check in on their crops and things like that. And that actually leads to what I was going to show you. It's my slide. So, we use virtual reality to fly our drones. And so let me just share screen. So here is an example of how we use virtual reality to fly our drones. So as some of you may be flying RC drones already, as you might know, you need a controller in your hand and you need a lot of experience in trying to fly these drones and stuff like that. But a lot of people may or may not have time to do that. So to address those issues, what we are doing in our lab is to use virtual reality, where all you have to do is to wear these virtual reality goggles and you're transported into a virtual environment where you can pick a drone with your bare hands, for example, and task the drones to do the things that you would like it to do. Okay, and the drones go out and they do what you want it to do. So that's another application of virtual reality and aerospace engineering, for example. And we see a lot of applications in real world for this one. Many different things. One example of that being, a user who wants to fly more than a single drone at one time. So we are able to do that within our confined space inside our lab, that a single operator, a single pilot can pick up and fly more than one drone at one time. It's not only that we can also have multiple operators fly multiple drones at the same time and exchange the drones between themselves halfway through flight. Okay, so the things that we anticipate these capabilities to allow people to do are things like monitoring infrastructure with multiple people who are geographically separated. So that's one of the big applications that we are anticipating these technologies to be used in. I'm pretty sure a lot of us have played tag when we were children. So one of the things that we are doing in our lab is to teach our drones to play tag with other drones. Okay, and the thing is this: when we play tag, we don't know what the other person is going to do. There's no communication between the other person and yourself. So you anticipate what the other person is going to do, and then you make your moves so that you can go tag the other person, right? And that's exactly what we are trying to do here with our drones. So we have a flight cage here at St. Louis University, and within that flight cage, it's a decent sized cage. It's about 150 feet long, 40 feet wide, about 40 feet tall, and it's a decent volume. So what we do is we fly our drones in this figure 8 pattern that you see here, and then use the 2 cameras that are on the cage to try and generate a ground track of the drones as they fly. And that's what you see here. The line in black is the ground track of the GPS of the drone that was flying. And the lines in blue and green are what the cameras and machine vision and AI behind that is telling me what the drone flew. Okay, with a little more training, we can see that we get a pretty good estimate of, it's a pretty decent estimate, let me say, of what the drone was doing while it was flying inside the cage. Now, one of my students right now is working on combining this information and some more information, everything only from video. Okay, there's no communication between the drone that's flying in there and us. And we're trying to figure out what exactly are flying and what its capabilities are, and so on and so forth. Now, I think I'm coming up on my time. Isn't that right, Amy?
Yeah, you're good. You're good. If we want to open it up for questions now, would that be?
So, yes.
Wonderful. So if anyone has questions, again, please submit those either to the Q&A through Zoom or on in the comments on Facebook. Dr. Guru Rajan, I just think the AirCRAFT lab is really, really cool. There's a lot of exciting things going on there. It seems to be kind of like the best of all worlds of engineering and aviation combined, and then being on the forefront of what's happening in our changing world. So I was wondering if you could talk a little bit more about the students who work with you in that research lab, and are they all aerospace students? How do they get involved? And how often do they work in the lab with you?
Okay, so the students who work with me have all backgrounds, aerospace engineering, electrical engineering, computer engineering, computer science, so these are 4 main, my students have, any of the 4 main backgrounds. Okay, so because the stuff that we do in my lab is a combination of all of these things. So, these drones can't just exist in a vacuum, and they can't be smart enough if they don't have a computer on board, which means I need somebody with electrical engineering and computer engineering to be able to design that and write software and all those things. So that's their background. How long do they work? Well, my lab does not have a specific time where you work. We work on a task line. So students are usually, when you first get into my lab, you are not necessarily assigned any particular project or task or something, okay? But in the first few months, 3 to 4 months or so, you work on and contribute to everything that's happening until you figure out what is the thing that you really, really, really like. And then, you pretty much take ownership of a particular project or a component of a project. Once you start taking ownership of a project, it's all task-based. So, work as long as it takes to finish the task. If it means you have to work 10 hours a day, it takes 10 hours a day. If it means 4 hours, you get it done in 4 and move on to the next task. So that's how, the work culture in my lab is just get it done,
Excellent. Yeah, so it's a great preparation for career life as well, right?
I agree, yes. And I actually, a lot of my students who have graduated from my lab and they have been in industry, and this is anecdotal, but they've come back to me and said, work is boring in industry because I don't get to do as many things as I did when I was in your lab. So I'm going to take it as a compliment that, my lab keeps them interested and excited to do things.
Excellent. Yes, definitely a valuable experience. We had a question come in. So what do you think about young people, specifically ages 16 and older, becoming drone pilots?
Oh, I think it's a tremendous skill. You should. And that was going to be one of the things I was going to recommend. Even if you don't necessarily become a drone pilot for commercial purposes and all, flying drones is a great hobby. It's a great skill to have, and it's not necessarily super expensive. So if you are interested, you should pick up a drone and go fly it. Find a flight field close by. And the best part about RC flight fields is that the community is so interested in teaching new pilots. They would love and they would welcome you with open arms to teach you to fly these drones. So if you have a chance, do it. And if you get a pilot's license, part 107, then it's even better. And typically in my lab, if a student comes in with a 107, then that person has that tiny leg up to come into the lab.
Sounds great. All right, just one final question, kind of in the line of that, those certifications. What does it require to pilot a drone across the city? So across St. Louis City, can we take off from SLU's campus and head somewhere?
Nope, not right now. Not with the regulations that we have in place right now. But that's the future. It's going to, it's coming slowly, which is the right way to do it. Okay, the FAA is working on these things in a really phased and thought out manner. It's going to take years, but it's coming. It's not, but you can fly across the city right now.
All right. Well, we are just out of time now. I want to thank everyone for those excellent questions that came in. And thank you, Dr. G, for sharing your time with us and showing us around the lab today. So we hope that all of our viewers did enjoy this virtual visit to SLU's AirCRAFT lab and our aerospace engineering program. If you would like to learn more about the engineering programs at SLU, please visit slu.edu/parks. As always, you can reach out to us at our email address, parksevents@slu.edu, if you would like to connect further with our programs. For any of our teachers logged on today, we'd be happy to set up a virtual lab visit or guest speaker for your classroom, either this semester or sometime into the fall. Please just send us an email to get that scheduled. And this was the final session of our Parks weekly webinar series for the spring semester. So please remember to follow SLU's Parks College on Facebook, Instagram, and Twitter, and regularly check our webpage for updates on future events that are hosted by our engineering and aviation programs. We hope to meet you in person very soon, but this will conclude our webinar today. So thank you again and have a great weekend.
Thank you, Amy. Thanks for the opportunity.
All right, I'll see you.